Hi, everybody. Thank you for joining us today. My name is Aisha, and I'm one of your Solid State Circuit Society staff members. The topic of today's webinar is Webinars for Young Excellence, Digits of Doom, presented by Chris Mangelsdorf. Today's webinar will be a little over an hour, and we'll hold a Q&A session at the end of the webinar. Attendees of this webinar have the opportunity to earn a certificate of participation for attending this webinar. I will put a link in the chat box with instructions on how to obtain the certificate. The webinar video will be posted on the SSCS YouTube channel after the webinar. Please use the Q&A on your dashboard to ask any questions. I now invite SSCS Webinars for Young Excellence Committee member, Ka Meng, to introduce our speaker and give a few welcoming remarks.
Okay, thank you, Aisha. So, hello everyone, I'm Ka Meng, an assistant professor at University of Macau and also the co-chair of the IEEE SSCS webinar of Young Excellence Program. So I will be the moderator of this of the event today. Before we kick off the presentation, so I will start with a short introduction of who we are and what we do. As young professionals and students, you make up more than 30% of our overall membership, and you are the future of IEEE SSCS the society. So as the Young Professionals Committee, we strive to address the different needs and interests of our young members with initiatives like the webinar today. So selected, next one please. Next. Yeah, so select benefits of SSCS membership for YP members include the following: access to the resource centers, which contains technical tutorials, short courses, and webinars, subsequent to our technical journal, letters, and also proceedings, distinguished lectures in your local setting, opportunity to apply for various grants and awards, and also we have the online mentoring platform, which helps you to connect with mentors around the world virtually. So next one, please. So one of the key benefits of the benefit is the SSCS Cronus Mentoring Platform. So it's a powerful tool designed to facilitate effective mentorship relationship and drive the professional growth. So with the Cronus program, mentors can share their expertise, provide guidance, and offer valuable insight to the mentees. So it also promotes communication, collaboration, and knowledge exchange, fostering a supportive and dynamic mentoring community. So please visit the website here to know more about this platform and register there too. And next one, please. Another important activity is the mentoring event. So we will regularly hold mentoring events in major SSCS conferences such as the ISSCC and the VLSI Symposium last month. So the event offers also invaluable opportunity for aspiring professionals and students in the fields of solid state circuits to connect with experienced industry leaders and also the academic researcher. So during the mentoring event, so the participants have the chance to engage in one-on-one or small group discussion with the mentors who possess extensive expertise and experience in the society. So the upcoming one will be the European Solid State Electronic Research Conference. So please stay tuned for the update there. So next one, please. So last but not the least, we have host webinar for Young Excellence program like this since 2020, which is a quarterly webinar series dedicated but not limited to YP members. So this webinar series complements the monthly SSCS typical webinars, which focus on technical developments. So the list of the webinar we did in the past is shown in here. You can access the YouTube channel there. To access the a full list and also the record of the webinar in the past webinars. So next one, please. So as part of the webinar series, today we will bring you to the webinar on Digits of Doom by Chris Mangelsdorf. So we will delve into a crucial aspect of professional communication that often goes unnoticed but can have a significant impact on our credibility and also the reputation. So assume you are going now to put some result of your circuits in your report. So how can you know if a gain of the amplifier 10 dB is an accurate expression? What about 10.001 dB? So I believe it's an issue that most of us will encounter, reporting number with unnecessary precision, only to realize that later it has backfired, leaving others questioning our expertise. So fortunately, we have answers today. So we have the esteemed expert in the field, Dr. Chris Mangelsdorf. So Dr. Mangelsdorf received the Bachelor of Science in Physics from Davidson College, North Carolina in 1977, and a Master and Ph.D. degree in the Electrical Engineering at M.I.T. in 1980 and 1984, where he received where he held the first analog device fellowship. So he has been associated with analog device since the summer employment in 1918 and has been a fellow since 1998. So from 1996 to 2013, he worked in Tokyo running the Analog Device Design Center and then adding responsibility to the Shanghai and also the Beijing Center as the Asia Technical Director. And then in 2013, he moved to Analog Device in San Diego, where he engaged in the development of high-speed AD converters. And in 2020, so he retired from analog device. So actually, if you're a regular reader of the SSCS magazine, you should see his name very often as he has been writing the Shop Talk series in the magazine there. So now I think all of us are eager for the presentation from the speaker. Let's start the presentation now. Just a reminder, if you have any questions, please leave it in the Q&A box in the WebEx program. So we'll select it and deliver it to Chris after the presentation. So Chris, I will pass the microphone to you now.
Thank you very much. Good morning or good evening, everyone, wherever you are. I'm going to share my screen now. Okay, that came through all right?
Yeah, that's clear. Yes, we see that.
Okay, great. Greetings to everyone, and thank you very much for having me here today. You may wonder why I'm here. This is the Young Excellence webinar, and I am neither young nor excellent, but I have made a lot of discoveries over my career about what makes a bad impression. In fact, I consider myself somewhat of an expert. But as young professionals, this idea of an impression is very important because you're building, as you start your career, you're building a name for yourself, you're building a reputation. You want to impress your colleagues that you know what you're doing. So impression is very important, and that's what this is about. So I'm going to show you, first of all, how to make a bad impression using numbers. All right, let me advance this. Okay, so this is our agenda here. First of all, I'm going to give you an example, and then talk about what's wrong with having too many digits in your work. After that, hopefully, I will have convinced you. Then we'll talk about how to manage that. You know, how to tell what the right number of digits are. What happens when you do mathematics with significant digits? How to manage all that stuff. And then finally, I'll conclude with an apology. I mean, a summary. Okay, so as engineers, oh wait, I'm going to reset my timer here. As engineers, we value, among other things, accuracy, precision, thoroughness, attention to detail. All of these are excellent qualities in an engineer, but sometimes we overdo it. Okay, now here's a scene I've staged, and one of our young colleagues here on the right has gone into the shoe store, and he says, okay, my shoe size is 10.314. Okay, now this young dude is pretty proud of himself. He's done his research. He's calculated exactly what his shoe size is, and he thinks that he's pretty hot stuff. And he says, wow, this salesperson must be so impressed. He probably wishes he was as thorough and precise as me. When in fact, the salesperson's reaction is more like, this guy knows nothing about shoes. I wish my shift was over. Okay. And I'm afraid the salesperson is right. I mean, as we know, shoes only come in half sizes. Okay. So all those digits are not really required. Sizes vary from brand to brand. So it doesn't matter what you calculate. And finally, if you've ever been on an airplane, you know that your feet actually change size. So, you know, all that extra precision this guy used did not impress anybody. It just made him seem like a doofus. Okay, so the conclusion is that using too many digits does not make you look good. It makes you look clueless. All right. And that's the major point. And if you've got that already, you can sign off. But if you want to stick around, um, first of all, I'll explain why. And I'll give you some examples that may convince you this is a bigger problem than you thought. I mean, you're probably thinking about that shoe guy going, oh, come on, I would never do something so stupid. But the fact is, we do it more than we realize, and I'm going to show you and hopefully convince you that it's a problem for all of us. Okay, and then finally, how to manage those extra digits. All right, so that brings us to the second item here. What's wrong with those extra digits? Well, extra digits are noise, they are context dependent, or they are irrelevant. Um, and what I mean to show you is that beyond a certain number of digits, what the other numbers are superfluous, they're meaningless. And worse than that, if too many digits will advertise a precision or an accuracy that you don't really have. Okay, so basically it's kind of a dishonesty. Right now, I've chosen an example here of a spectral plot from a paper I chose at random, pretty much, from the IEEE database. You know, and I chose the spectrum because that's something we're all familiar with, and I think we can all relate to these issues. So here's a publication, and the person or the group who did it, they say up here at the top, SFDR, that's spurious free dynamic range. This is an ADC, and it's 97.82. Well, you know that's right because here looks like the reading of the instrument right here. It says minus 97.82. So yes, it must be 97.82 dB of difference between the fundamental and this harmonic. Okay. But the question is, do we need 4 digits here? 97.82. Is that really required? And this is not unusual, by the way. You can find this all over the place in papers and data sheets and so forth, 4 digits for the spectrum. But what does that actually mean? Okay, so if there's 4 digits, the implication is that it means something, right? So in other words, there's a significant there's a difference between 97.82 and just 97.8. In other words, that the implication is that 2 was added for a reason. All right. And so the other way to look at this is, well, okay, if I round off this 97.82 and just make it 97.8, how much difference would that be? Okay, so that's what I've done here, calculated in terms of the difference in amplitude. It's only 0.2%, right? So you can see here that this, if I round off this number by one more digit, make it only 3 digits, change the accuracy by 0.2%, which is not very much. So you could say, okay, well, we can round that off because it's not a big error. And then you say, okay, well, what if I rounded off 2 numbers? Okay, and so instead of 97.82, it's just 98. And by the way, this is called rounding. And if you're not familiar with that, send me an email because this is kind of important to this principle. But anyway, if you do the calculations and work it backwards, the amplitude difference for rounding off to or only using 2 digits, your error is 2%. So you think, well, okay, so 2%, it's starting to get serious. I don't think I want to go that far. But if you think a little bit more deeply about it, you realize that 98 dB is 78,000 times, okay? This little harmonic here is 78,000 times smaller in amplitude than the fundamental. And if you then figure out what does that mean in terms of this last digit, what does that actually change? So you look at this last digit here and look at the difference between 97.82 and 97.83, and you see that's the difference in 0.1053 LSB versus 0.1057 LSBs in a 14-bit LSB, which is what this is. That's 0.004004 of an LSB. A tiny, tiny little signal. Okay, so given all that, I mean, do you really need that kind of precision? I mean, do you really need 0.004 of an LSB to describe the amplitude of that harmonic? I don't think so. Okay, so one quick way to check this, okay, to check if you're working with too many digits. One quick way to check this is just to push the button again and take another measurement, right? And I'm willing to bet that in that paper that we had in the example, if they did another measurement, the last few digits would be different, okay? So you push the button again, you get a different measurement. Well, that means, you know, the digits that are changing are just noise, right? I mean, it doesn't even, it's not even repeatable from sample to sample. So you push the button again and you get different. Another thing that those extra digits may represent are even worse, because with noise, when you have noise, you can average it, and voltmeters and things do that kind of thing. Even the FFT does it to a certain extent. But if the number that you measured includes some instrument error or systematic problem like offset or gain error or drift, those extra digits are really just documenting that, and that can't be averaged out no matter how many measurements you take. So it could be bad. Another check you can do, okay, when you've got this measurement, another check is to change something. For example, you put on a different cable, you adjust the room temperature, you put in a different sample, okay, and you start getting different answers, okay. That means that all those digits that are changing, that aren't constant, are really dependent on the context, you know, the situation, the environment, perhaps, you know, and while even if you don't have any noise and your measurement is perfect, you're going to get errors due to these kind of things, or get differences in the result due to this. So the extra digits aren't conveying anything about your silicon. They're talking about the measurement setup, for example, or the room temperature, or which sample you used. Okay, so here's an example of some real data. This is one distortion component from an input, full-scale input. And these are averaged FFT measurements, which means that the noise here has been suppressed. So this is not noise. But you can see just measuring this one thing, I mean, this is a different kind of minor condition changes, okay? And it spreads the data all over the place. I mean, even one measurement run over different input frequencies is all over the place. My favorite one here is these two blue lines, okay? And what I did there was I reversed the balun. The balun is a transformer on the input that converts a single-ended signal into a differential signal. Okay, so you have a differential signal out, and all I did was flip that over, okay? And that was enough to cause this difference of like 10 dB, okay, in the results. Okay, so when you look at this, what's the point of the extra precision, right? Okay, so this sample right here, The measurement system and all the FFTs and so forth tell me this is minus 64.3636, etc. So what? I mean, it's that measurement. That measurement may be perfect, but it doesn't really represent what you're trying to communicate. Okay, about doesn't say anything really useful about the device. Okay, so the third check, and this is a biggie, ask yourself what the application needs. Because a lot of times what you find is that those extra digits that you've got there are really irrelevant. You know, if you look at what the customers ask for, okay, here's your demanding customer, and this is their receiver they're designing, and you know, you look at the specs that they're trying to achieve, right? And you get, oh, okay, I need about 10 dB of gain here, or I need a noise figure of 28 dB. You know, I have all these kind of dB in round number, and nothing, you know, about oh, I need you know, 9.95 dB. No, it's not like that. So the customer is thinking about this in terms of round numbers of dB. And, you know, because the reason for that being that they know that, you know, you know, it depends if you change the board, you know, it gets a little hotter, you place two wires too close to each other, things change. I mean, it's hard to get any kind of real precision here. In fact, many years ago, when we were doing converters in the megahertz range, we used to speculate about what we would need to digitize a gigahertz. Okay, and of course we can do that now, but we couldn't at the time. And one of the gurus at the in this whole RF stuff, one of the gurus said, "Well, we're only going to need 4 bits for our ADCs, and that's because our connectors are no are no better than 4 bits accurate. The connector, in other words, the connector changed the signal so much that it was unpredictable, and 4 bits was good enough for an A to D. Well, of course, over the years, you know, connectors have gotten better and ADCs have gotten better, but it just shows you the point that the RF guys, the people that are going to use these DAB numbers, um, uh, don't think of them in terms of precision. They think of them more in terms of just kind of an order of magnitude. In fact, if you think about what the decibel means here, you know, the dB, when you're talking about amplitudes, it's 20 times the log of some ratio generally. And so what you're saying is, okay, what is the power of 10 that my ratio represents? Okay, is it's basically an order of magnitude kind of tool. What is the order of magnitude of my signal here? And if you break it down, you know, this high precision, you get the integer part here, which is a very good approximation to the original number. And then you get this tiny little correction factor, which is the fractional part of the dB. So you can see that this is the important part. These extra 2 digits here are not much of anything. In fact, you may know that when you take a logarithm, the fractional part is called the mantissa. And did you know that the original meaning of mantissa in old Latin or Etruscan or whatever it was worthless addition. So even the name mantissa makes it sound like an appendix, like something not useful. Okay, so DB, I think if you look at how DBs are created or what they mean, it's kind of an order of magnitude thing. All right. So finally, let's talk about simulators. All right. Simulators don't know about the precision of a number and they don't care. They treat all numbers the same and they just crank them through. So in this simulation, which incidentally, this simulation goes with the block diagram I showed a few slides ago. Has all these ridiculous digits. I mean, 7.12 times 10 to the minus fourth. Please, let's just call that 0. Um, it's out of control. And I think maybe the person who published this table wanted to show these extra digits to show that the simulator was actually doing something. Because otherwise you end up with round numbers and you can't tell that the simulator is working hard. So maybe that's what they meant. But the point is, simulators are not the right place to look for what precision should be, because they don't know the difference between just a guess and a NIST standard number. So simulators are not to be trusted in this department. All right. So just in case you're thinking this is only about DB, I have another example real quick here. And this one is a prediction of metastability. Metastability is when a comparator is too close to its threshold to be able to regenerate a definite answer in the allotted period of time. Okay, and these are rare events, but they cause errors in the system, and so you need to predict what they're going to be. So anyway, I found this scholarly paper, which was very good in all other respects, but they were quoting the probability of metastability to be 8.11 times 10 to the minus ninth. Okay, so I thought to myself, what's the difference between 8.11 and 8.1 times 10 to the minus ninth? Okay, so again, I'm testing the value of this last digit. They put this last digit in there. Does it have any value? Well, if you work the equations backwards, okay, and I didn't show it here, but you come down with two time constants, okay, associated with each problem. And so these two numbers are associated with time constants that have a ratio of 1.00005 or 0.005% difference. Okay, so these two time constants, the time constant represented by 8.11 times 10 to the ninth and 8.1 times 10 to the ninth are different by 0.005%. In other words, that's how much this last one is adding to the precision of the number. Okay. Now, these time constants are just GM and C. There's no way you know these to this kind of accuracy, right? You're lucky to get 20%. Okay. So there's no way you know these numbers at that kind of accuracy. So there's no way that you should use two decimal places to represent the number, right? Because you don't have anywhere near this accuracy. Writing the number like this implies you know it to this degree of certainty, and you don't. In fact, if you raise the temperature, or when I did it with my own circuit, raising the temperature from 27 to 100 degrees increases that time constant by 40%. And that's 100,000 times increase in probability. So, using these four digits just doesn't make sense. And here's some more real data to show you what the real world looks like here. And you can see that the data is kind of all over the place. It does not match the calculation. It depends on all kinds of things you don't understand. But it's valuable data, but it's not good. The data is not good anywhere to two decimal places. Okay, and the problem is, so the reader seeing this to two decimal places thinks, well, these guys maybe they don't have a good understanding of metastability, or maybe they don't have any experience with it. To quote that kind of accuracy, right? Because the real world is much more messy than that. All right. Okay. Now we're going to talk about making this a little bit more formal, and I'm going to show you how to choose digits and how to manage them. But this would be a good time to break in if you have a question. I don't know if you can do that, but you may be muted. But if there's any questions right now, I'm all ears.
Yeah, maybe we can go ahead first, and then we will leave the Q&A session after the presentation.
Or roger that. Okay. So let's talk about significant math here. And I'm going to start off with an example measurement because this is kind of critical to the concepts I'm going to be discussing. So I'm going to discuss a highly technical measurement that you might make in the lab. Okay. Let's say that you wanted to measure the length of this Twinkie, and the Twinkies are these guys here. You want to measure the length of this Twinkie, and it's important because you need to know if this is going to fit into the lunchbox. So it's a critical measurement here. So you get out your yardstick and you hold it up to the Twinkie and you say, well, okay, it's about 10 centimeters, right? It's about 10 centimeters according to this, right? You get a little closer and you say, I think maybe that's a little less than 10 centimeters. So you get another ruler and you look at it, and sure enough, you say, okay, that is 9.9 centimeters. All right. And then you get down, maybe you take off your glasses, you get down and you look real close, you say, okay, it's between 9.9 and 10. And to me, it looks like 9.94 centimeters. Okay. So that's the best I can do. I can't get it more accurate than that. Okay. And then the ruler slips. Okay, and it moves to a different place. And then you think, oh nuts. Now I've got a completely different measurement. Right. So this little exercise, the point it illustrates all the important points of the significant digit thing that I want to introduce here. First of all, the last digit of this measurement was an estimate, right? I was sure about the first nine, then the 0.9, I was sure about that, but the 0.4, I was kind of, there's no markings on the ruler. I just kind of say, well, but it still has meaning, right? That's the important thing because it says it's, kind of between 9.9 and 4, or 9.9 and 10. And it's 4. It's not 2. It's not 8. It's 4. So it still carries some meaning, even though it's not very precise. All right. So the other thing that we notice here is we have 3 useful digits, right? If I add any other digits here beyond this, they mean nothing, right? Because this 4 was an estimate already. So if I say 4.5 or 4.90, none of that can mean anything because this 4 itself was an estimate, right? So anything beyond that is useless. It's also very interesting, and this is kind of a practical observation, that there are very few things in life that are worthy of more than 3 digits. And that is a powerful thing to know when deciding on the number of digits you use. If you have a number with more than 3 digits, you may want to take a closer look and make sure that they really represent something useful. Okay, because just as an observation, most things are not more, we don't know most things to more accuracy than that. Okay, and it finally, it illustrates what the thing I was calling context before, where you measure, where the ruler is beside the Twinkie, or how old the Twinkie is, or so forth, affect your measurement. Okay, so this is another thing that this exercise indicates. And finally, it illustrates that it doesn't matter because the lunchbox itself is 23 centimeters long. Okay, so of course it would fit. And it says that if we had stopped at the very first measurement, where we just looked at the meter stick and said 10 centimeters, if we had stopped there, that would have been good enough, right? That first measurement, just one reading, would tell us that it would fit, and the rest of the stuff, this 0.94 here, doesn't really matter. And these are the topics that I will continually come back to in here. Is, you only have 3 useful digits. Anything else is noise. Depends on where or when you measure it. That's a context dependence. And the fact that it doesn't matter is means it's irrelevant. Okay. So to deal with this, over the years, people have come up with some conventions, and it's known as significant digits or significant figures. And significant here means they carry meaning. These are digits that carry some important message, and they carry an implied precision or accuracy. Okay, so these are the important digits, the significant ones. And it turns out that the first person to study this seriously was our good friend Carl Friedrich Gauss, one of the greatest mathematicians of all times, you know, for his contribution in astronomy, magnetics, statistics, non-Euclidean geometry. He's the father of mathematics here. But he was the first guy to kind of study this seriously and think about what it means. And over the years, from Carl and people that have come after him, we have a set of rules for these significant digits. But I don't want you to freak out about this. I mean, this is not a lot of stuff you need to memorize. These are conventions, not laws. They're intended to help us communicate, you know, to indicate the relative precision of our numbers. Most of these rules are kind of intuitive or common sense, so you don't really need to memorize them. You'll be good without doing that. And the usage considerations are always more important than these rules are. Just because you have precision of 5 digits doesn't mean you need to use it, right? And I'm thinking again of like the dB, right? You may actually have more precision than you talk about, okay? And that's fine because people don't want to be bothered with too much precision. They really want to know if it's 78 dB or 90 dB. So usage considerations are important. All right. So these rules are like this. First one is only the last digit contains any uncertainty. And this is this we learned during our Twinkie measurement here. These first 2 digits are certain. This one is an estimate. It's not really a guess, but it definitely contains uncertainty. Okay, so that's all of significant digits that will always be true. Or and you shouldn't write more digits than this unless they're significant. Okay, rule number 2. All non-zero digits are significant. Okay, so if it's not a 0, it's significant. And so in this case, we have 3 significant digits. Now, zeros are tricky. And that's rule number 3 here. Leading and trailing zeros are not significant. And if you look at this first number here, 123,000, right? These zeros here are not, by convention, are not carrying any significance or any more information. They're really just placeholders that indicate an order of magnitude, right? So these aren't actual accurate measurements. These are just indicating an order of magnitude. So here's another example. This was leading zeros. And again, this 0 doesn't really convey any meaning except that it indicates the order of magnitude of these guys here. Okay, so it's a placeholder. However, when the 0 is between non-zero numbers, then it is significant. Okay, and in this case, we have 4 significant digits compared to 3 in the other 2 examples. Now, if you don't remember this rule, and there are some details to it, if you don't remember this rule, one thing you can do is convert your number to scientific or engineering notation. By engineering notation, I mean milli, micro, nano, pico, that kind of thing, right? And when you do that, you automatically strip off a lot of the placeholder things that just indicate order of magnitude. So for example, if you're measuring 123,000 volts, you write it 123 kilovolts. Okay, and now those zeros have disappeared. You can see, I've got 3 significant digits. Likewise with the second number, That turns out to be 12.3 millivolts. Again, you see it automatically, converting it to these units automatically kind of gives you a sense of what digits are important. But this bottom one, in order to convert that, you need to carry all 4 digits in there, and this 0 here, of course, doesn't disappear. All right, so this is a quick and easy test. If you're ever confused, try this, and that should help. Now, zeros, there's another tricky thing about zeros is that if there's a decimal point present, it changes everything. So as we said, this first one here is only 3 digits. These are just placeholders. But by convention, if you put a decimal point here, then that makes all of these zeros significant. So the person who wrote this number with a decimal point intended you to think that it was exactly 123,000, to the last volt or whatever. Okay, so this is a signal, okay, that these digits here are important. Likewise, this 0 here afterwards is also important, and so this has 6 significant digits. So it gets a little tricky here with the decimal point. But it's a question of communicating your intent, your accuracy. Okay, there is one other situation you need to be aware of here with significant digits, in that some numbers, called exact numbers, have infinite precision. Okay, for example, the year 1970. 1970 is an integer, okay, and it's exact. You don't have 1970.3, right? It's exact, okay, to infinite amount of precision, because basically you're counting something, okay? And unless you're counting Schrodinger's cats, this will be an integer, and it will be exactly an integer. So that's just infinite precision here. The second one is how many centimeters in a meter is 100. That's a definition. Okay, so that's infinitely precise too. Okay, you know that exactly to an infinite number of places. Pi, or a constant like e, the base of the natural logarithms, those things are constants that do not change, and we know billions of significant digits for pi, and we haven't found them all yet because they're an infinite number. Okay, so but that one, pi is always infinite precision. And finally, numbers that are used in a formula like this are exact. So in this formula here for surface area, 4 and pi and 2 are all exact numbers with infinite precision. R is probably not, because that's most likely a measurement, okay, it represents some real quantity. But in the formula, these other numbers have infinite precision. And notice that none of these numbers is a measurement, right? Most of this significant digit things has to do with, measurements or other sources of uncertainty. Okay, none of these, I mean, sort of the year is counting, which is kind of a measurement, but not really. So anyway, none of these are measurements. Measurements is when this stuff gets really tricky, right? So that the basic rules, again, for summary, are only the last digit is uncertain. All non-zero digits are significant. Leading and trailing zeros are not significant unless there's a decimal point present. Okay, so on we go. Now, if you want to do math with these, it gets kind of interesting. You when you start to think about the significance of what the digits are in your number, it can get a little tricky here. So here we're measuring, multiplying 2 numbers. Okay, the one on the top has 5 significant digits. The bottom one here has 3 significant digits, and you can see that I've indicated the uncertain digit with yellow. So whenever you multiply a number times a digit that's uncertain, that entire product becomes uncertain. Okay, so I've written out the entire multiplication here, kind of longhand, and you can see that 3 times this top number gives you all this, but they're all uncertain. They're all infected by the uncertainty of this 3. When you do the multiplication times this second digit here, only this last digit from the 5 is corrupted by the uncertainty. So you can see here that for this line, only the 0 is uncertain, and likewise for the 1. Now, when you add all these partial products together, you anytime you add in an uncertain number, the result's going to be uncertain. So you add them all up, and then all of these numbers are uncertain. That means that you need to round this up, right? And only keep one digit, right? Because this is the last, only the last digit can be uncertain in the significant digits. So you end up here with 3 significant digits, right? Because you had to, these all got to go, right? And this one you round up, you got point, you got 8 here, so you round up to 2. So you have 3 significant digits. And this is not unusual to see that you start out with 5 significant digits and 3 significant digits. Your answer is in 3 significant digits. That's not a coincidence. And the general rule here is that this is the general here. Calculations don't increase precision. Results generally have the same number of significant digits as the least precise operand. So for example, if you multiply 1.23, 3 significant digits, times pi, which is an infinite number of digits, then you only get 3 significant digits still. Even despite the fact that pi has an infinite number of significant digits, your answer only has 3, same as your least precise operand. Okay, that's that's a general condition of doing mathematical operations on significant digits. Okay, so let's walk through an example. We're almost done here, but let me walk through an example. What does this mean? Okay, what is 4 times pi? Okay, now this is using our newly acquired significant digits thinking here. The, using the idea that okay, 1 digit here, there's no decimal points or zeros or anything like it. There's nothing else. We just have 4. So that is 1 significant digit. Okay. So when we multiply it times pi, our answer, using this general rule, is going to be 1 significant digit, right? So that means 4 times pi is equal to 10, right? Because there's no decimal point here. So this 10 is only 1 significant digit, right? So that's one possible answer. Okay, now if this 4 times pi is in a formula like this 4 pi r squared, okay, then it's exact, right? Because this is not a measurement. This is a constant dictated by geometry. Okay, so 4 times pi is an infinite number of significant digits, right? Because both this 4 and this pi are exact numbers. Okay. And okay. Then another way to think about this, if you don't know the situation about, what does this 4 represent? Where does it come from? Well, you can kind of estimate that this, if you think this 4 is really the round off of a number that had more digits, then you know that it's probably between 3.5 and 4.5, the real number, right? Okay, you got a 4 here, but you're estimating or guessing, or perhaps that the number is really 4 is representing some quantity between these 2 limits. So work that through. Okay, how much is 3.5 times pi? How much is 4.5 pi? You see that the difference or the inaccuracy is here in this digit. Okay, so that means you can only keep, this will be the last digit you keep, right? So you round off the exact answer, which is 12.56, blah, blah, blah. You round that off to 13. Or you could average these two numbers. But anyway, this gives you two significant digits. And finally, there are actually calculators that operate on these significant digits. There's quite a few of them, actually, and I've got one here from omnicalculator.com, and it's kind of interesting to see what this does. And this software just interprets the rules kind of blindly, Okay, it says 4 times pi here, and only used the digits I could remember. 4 times pi, okay, that means that's one significant digit, right? And so then it does, okay, 4 times 3.14159. Okay, and notice, I don't know if you can see, the screen's a little small here, but there's an underline under the 4, and there's an underline under the 9. And then when you get the product here, you get an underline under the 1. And then that underscore there is saying, it's a notation that some people use to indicate the last significant digit, okay? The digit that has the estimate in it, that's the last one. And so in this case, you can see that underscore has been moved to the first digit because the 4 has only one significant digit, moved to the first digit. And so when you need to round that number off to 10. Okay, so this gives us the same answer we got in the first case. But if you ever get kind of stuck or curious or encounter some special case, you might you can either look up the rules of in detail for significant digits, or you can try one of these calculators. So when we look at the results here, we have 4 different results. 2 are the same, but the important message here is that the results depend on your interpretation or your knowledge of what the 4 represents. Okay, so this is not, again, this is not a law. Okay, this is a convention. The significant digit stuff is a convention that's to help us kind of communicate and project the right levels of accuracy and not mislead ourselves or others with too many digits. Right? So in summary here, the important conclusion, hopefully, that I persuaded you, is that using too many digits does not make you look good. It makes you look clueless. And the reason for that is that to get the right number of digits, you need to know where the number comes from, okay, how it was created. And you also need to know how it's going to be used. So if you get the right number of digits, then it kind of tells people that you understand what the number, where the number came from and how it's going to be used. If you get the wrong number of digits, then it kind of shows, I mean, wrong in by a lot of digits. You get one wrong, maybe not too bad. But anyway, using the wrong number of digits sends the opposite message, like, I don't know much about this. I don't know where this number came from or how it's going to be used, right? So you don't want to do that. So when working with numbers, there's only 3 things I think you really need to remember. And the first one is the last digit should have uncertainty, right? Okay, that's a quick check, and that's kind of common sense in a way. If you're ever asking yourself or find yourself in some sort of quandary about how many digits your number really is, try putting it in engineering notation, and that may give you a good indication of where it should be. And then finally, as I mentioned earlier in the talk, there are actually very few things that are worthy of more than 3 digits. So if you find yourself with 4 digits or more, you should probably step back and think, what, do I really have that much accuracy? And finally, you want to ask yourself these three questions. You know, what is the accuracy of what I'm measuring here? Do I really know it to this accuracy? What is the context? In other words, if I measured a different piece of silicon, or I measured it on a different day, or I measured it with a different cable, would the number be different? Then I'm probably using too many digits. And finally, how is this number going to be used? You know, what do people need? How do other people think about this quantity? Okay, so if you think about you can study the rules if you want, but these are the important points, and if you follow these, you won't get yourself into any serious trouble, and you will make a good impression. So I thank you very much for your attention, and I thank the organizing committee for inviting me. I guess we can take some questions now.
Okay, so thank you, Chris, for your insightful presentation. So now we will do the audience Q&A session. As a reminder for our audience, please use the Q&A box to ask any question you have regarding to the topic we had today. So we will have the first question first. So actually, in some point in your presentation, you mentioned that zeros with decimal point and that contains significant digits or that contain significant meanings. So how does that change, or will you elaborate on that point?
Okay, let me zoom back there. Like this one here.
Yeah, exactly.
Yeah, so it again, this is not a kind of a mathematical point, you know, that you can some theorem or something that you can prove or something. This is just a notational convention, okay, which says, you know, that this number 123,000 written this way means, yeah, 120, you know, it's in the thousands, okay, right, hundreds of thousands, right? When you put the decimal point there, you mean, no, I'm serious. It's exactly this number, right? And likewise, if you put a zero after the decimal point, that means, no, I know this number to 0.1. I know it with more accuracy. So it's not, it's not anything we're doing mathematically. It is how these numbers are interpreted and how they're written. Okay, it's not again, it's not a law. Does that answer your question?
Yeah, I think so. So actually, there's one audience asked the questions that I never encountered this before. So he mentioned standard rounding practice is to round up the next digit, 5 to 9. So the audience said one thing he learned in the high school is that they round up to the nearest even digit. So for example, 23.5 round up to 24, but 24.5 also round to 24. So, and he mentioned there were minimize the approximation error. So do you have any thought on this one?
Yeah, so rounding up to the nearest even
Digit, yes, only round up to the even digits.
The next whole digit. I mean, even if it's odd.
Yeah, I think so. Yeah.
Okay. Yes. Well, it depends. Let me see if I can navigate this well enough. To show you an
actually for me,
example.
this is something new. Yeah.
Yeah. I can. Okay, is that up? You see this the slide here about rounding off?
Okay.
Yeah, does it am I sharing correctly? All right.
Yeah,
So
I can
this
see your slide.
this is this shows about how rounding off. and rounding off doesn't necessarily happen at I need my pointer. Doesn't necessarily happen at the decimal point. Rounding off happens when you need to remove digits. You need to truncate digits, right? And if you want to, in this example here, let's say I decide that the last really significant digit is 6. Okay, the rest of the stuff is garbage. So I need to cut this off, right? So to do that, I look at the next number, and the next number is 3. Okay, so it's below 5. So I just throw these digits away and leave the 6. However, if I wanted to round off to this place, okay, so I need to truncate these digits, then I look at the next number and it's 6, and that's above 5. Okay, so 5 or above, I need to round up. So you notice I changed that 6 to a 7, right? And here's another example right at 5. 12.5 rounds to 13 because it's 5 or above rounds up, 4 and below rounds down. So that's even though it's not a whole digit, right? As this case is, this last case, but up here, for example, you're going to truncate this number to a certain number of decimal points. I think that's the question, right?
Okay, yeah. So thank you. So we have next question, a more specific one. So let's say we have a numbers 123,000. So how do you indicate if it is a 4 or 5 significant figures if we didn't given any clue on this? Yeah,
So
like
say-
1, 2, 3, 0, 0, 0.
Okay. Let me go back to that slide. Bear with me just a second.
Okay, no problem.
Got it? I got it.
Yeah.
Got it.
So exactly.
Okay, so the question is,
So like for your number on top, so can you indicate if it is 4 or 5 or 3 significant figures or even 6? Just with
Right.
the number here, yeah.
Right. I think the question is, if this number here with these trailing zeros, no decimal point, is 3 significant figures, right? When you put the decimal point, it becomes 6 significant figures, right? Now, I think maybe the question is, what if I wanted 4 significant figures?
I think what he means that if we just have the number on top 1, 2, 3, 0, 0, 0.
Yeah.
So can we tell if it is 3 or 4 or 5 or even 6 significant digits without any explicit clue on the available significant digits? Or we can we tell from the number itself just?
Right. Well, yeah, I mean, this, I think that the clue is this decimal point, right? Okay.
Okay.
It's saying, yeah, okay, these numbers are important. This number is precise. Okay, we want to include these zeros, so we put the decimal point there. Here they're not. They're just saying, it's like the national debt, right? You ask what the national GDP or something is. You don't give it to the last dollar. You just say it's so many billions, right? Well, this is the same thing, right? It's just 123,000, right? So the tricky part comes when you want to indicate, instead of like 3 digits or 6 digits, you want to indicate this number with 4 digits, right? How are you going to do that? And I think there's several ways you could do it, but writing it as kV, for example. So if you write this 123.0 kilovolts, okay, if you write it that way, you can indicate that this zero is significant, okay, but these two are not. Okay, that's a way you can write it, to show that zero is significant and you want it included. So if it's 4 significant digit, the best way to write it is probably 123.0 kilovolts.
Mhm.
Is it?
Okay. Yeah.
Yeah,
I
so
agree that the
so
zero is quite tricky. Yeah.
right, right. But again, what you're doing is you're conveying the meaning of those digits, or the accuracy of your answer, right?
Mhm.
Or the
Yeah.
accuracy of this number. And um, it's 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 kind of a convention. It's not a law.
Okay. So we'll have one more. We'll actually consider your experience in the area. So, you have any occasion on that using too many digits in our measurement or reports negatively impact the professionalism or the credibility?
Yes, yes. Well, I think I had the one example about the probability, the metastability,
Mhm.
and that to me is, I mean, I know the guys who wrote the paper and they're excellent engineers, so I knew different, but still it gave me a kind of prejudicial feeling about the authors. My reaction was, these guys don't know what they're talking about, right? I mean, they do know what they're talking about, and they actually had a reason for using those digits. Um, but the point is, that was the kind of impact it had. And when you're reading papers or looking at somebody's results, and they put down too many digits, you think, oh geez, this person doesn't know what they're thinking. So I've I've seen I've seen many times, in situations like that, people don't usually say something. Occasionally, since I'm such a jerk, I make a snide remark, but people don't say anything, but they're thinking, oh, that's not right. That isn't good. Um, so that's one aspect. Another aspect of it is, when I find myself doing it, one place where I found I've done it is, I'll be putting together a schematic, and I need a certain size capacitor. So I calculate and I calculate and I do simulations and I come out with a number, and I want exactly this capacitance, right? And so I put it down to maybe 3 or 4 decimal places, thinking, well, you know, I don't know exactly what the accuracy is, but this is where I want, this is the middle. This is where I want the layout engineer to aim for. Um, and the problem with that is that it's it's a I'm kidding myself. Okay, I'm not being realistic about what's happening here. Because there are all kinds of limits and all kinds of tolerances on that number, so that a lot of precision just doesn't make sense. I'm kind of saying, oh well, I know that, but I'd like this to be the center of the distribution. No, you're kidding yourself, and that's a dangerous way to think. You need to, when you're designing stuff, you need to keep in mind that you don't know these numbers to infinite precision. The tolerances on things like resistance and capacitance alone can be like plus or minus 20%. Okay, so putting down 4 digits, 5 digits, just doesn't make sense. You can get those numbers, you can get as many numbers as you want out of the simulator. I think the simulator, a double precision floating point number will give you like 16 decimal digits, right? The simulator doesn't care, but you should. You should keep in mind these numbers are not that accurate, right? So it's an important mindset for for ourselves, even if we're not thinking about the impression that it makes. So those are 2 aspects.
Okay, yeah, thank you. So, thank you for addressing the question. And unfortunately, due to the time limit, so we will now end the Q&A sessions. So, and on behalf of the organizing committee, I would like to appreciate Chris again for sharing your insights and perspective in the webinar today. So it will, the suggestion and the opinion will inspire and guide the audience about the journey. So the record of this webinar will be available in the YouTube channel later, so you can access the channel to get the recording. And so that's all for the webinars today. So have a good day and bye.
Thank you very much.
Yeah, thank you very much. Bye.